Welcome to the deep dive. Picture this. We're actually getting serious about building off-world. You know, habitats on the moon, maybe Mars. Structures that can actually protect people long-term.
Right, proper shielding, living spaces.
But the big question is always, where do you get this stuff to build with? I mean, tons and tons of concrete.
Yeah, hauling that from Earth, just forget it.
It's impossibly heavy. The cost is, well, astronomical.
A logistical nightmare, basically. Every single kilogram launched costs a fortune. So if you want to build anything more than, say, a tiny landing pad...
You have to use what's already there.
Exactly. You've got to work with the local environment.
Which is, of course, ISRU, that whole idea.
In situ resource utilization, using the dirt, the rock, maybe water ice if you find it.
Yeah, turn that loose stuff, the regolith, that moon dust or Mars soil,
into something solid, something you can build with. That's the challenge.
Right. And people have proposed different ways. Melting the regolith
requires huge amounts of energy.
Chemical reactions.
Can need lots of water or heavy, complex machines you still have to ship out.
So this deep dive, we're looking at something called StarCrete. And it's based on a surprisingly ordinary ingredient.
A really different approach, it seems. Yeah, the binder, the glue, isn't some complex chemical. It's based on starch.
Starch, like from the kitchen.
Pretty much. The kind of thing you'd find in food.
Okay, from food crops.
Mm-hmm.
Right, let's get into this. We've been looking at a research paper. They explored using starch to bind simulated moon and Mars dirt.
Mm-hmm.
So our mission here is to unpack the science, see how the StarCrete measures up, and understand its unique points. Some are quite unexpected.
It's a fascinating concept. It's sort of like other biopolymer ideas we've heard about, using an organic material to stick the regolith particles together.
Like Martian biolith that use cheetah sand, right?
Yeah, or those ideas using protein binders derived from things like human blood plasma even.
Ah, yes, the blood plasma concrete, always a bit problematic.
Well, yes. Using human plasma is efficient in one sense, but it's not exactly a surplus resource, is it?
It's not in a small crew. And potential health risks, too.
Definitely a key point. Starch, though, that's something different. Any long-term habitat anywhere off-world is probably going to produce loads of it.
Because you're growing food, right? Staple crops.
Exactly. Potatoes, rice, corn, whatever works. You're growing it to survive. And you'll absolutely plan for a surplus. You have to. But to manage risk, if a crop cycle fails or something.
Okay, here's where it gets really clever. That surplus starch, which you already have for food security,
becomes your building material.
It connects food and shelter. Two critical systems, fundamentally linked.
Precisely. And that avoids needing completely separate systems. It simplifies the logistics, cuts down launch mass, lowers cost. You're basically using the waste or surplus of one essential system as the input for another.
Okay, so the researchers took this idea and really ran with it. They started with something like corncrete, I think, using cornstarch.
Yeah, but they found potato starch actually worked much better, so they renamed it StarCrete. And they really dug into optimizing it. They used a systematic approach, testing lots of variables together.
To find the best recipe.
Right. First, they screened different starches. Potato starch was the clear winner. Much stronger initial results.
Why potato starch? What was special about it?
The paper suggests a few things. The granules are larger, apparently. It also has a lower gelatinization temperature. That's when it swells in water and makes a paste.
Okay.
And higher phosphate content. Plus, it made a really viscous paste, which seems to have been important for binding.
Right. So they had the best starch. Then they started adding things.
Yeah, and this is where the research process gets interesting. They tried additives, things you might find in space or easily make, like salts found on Mars, MgCl2, magnesium chloride, acetic acid, which you can actually make from starch itself, urea, from urine processing, even human saliva.
Seriously?
Huh. Yeah, the idea was maybe the enzymes could help break down the starch or something. And initially, things like urea and acetic acid seemed promising. They boosted the strength in earlier tests, but in the later, more detailed optimization experiments, where they tweaked ratios, water content, temperatures, drying, they found the opposite.
The flip. Always happens in research.
Yes. Contrary to those first results, urea and acetic acid actually reduce the strength in the final optimized process. But magnesium chloride, MgCl2, which looked bad at first,
turned out to be good.
turned out to be beneficial later on. It really shows how crucial that detailed optimization is. You can't rely on early screening alone.
So they could drop the urea and acetic acid,
Yeah.
maybe avoiding issues like toxic gas release at processing temperatures.
Exactly. And focus on leveraging that MgCl2.
What else did they figure out during optimization?
Higher temperatures and longer times for that initial heating step, the gelatinization, were really important, and they found something quite clever about drying it. Fully drying the material after making the paste didn't hurt the strength. And then slightly rehydrating it just before the final compression step actually helped.
Huh. Why is it good?
It meant they could use more water during the initial heating, which was good for gelatinization, but then use less water for the final forming step, which was also good. It sort of decoupled those two stages.
That is a neat trick. So, after all that tweaking, potato starch, regolith, so what kind of strength did they actually get?
Okay, so for the simulated Martian regolith, they were hitting compressive strengths around 72 megapascals, 72 MPa.
And for the moon simulant?
Well, even better, around 92 MPa.
92. Okay, let's get some context here. How does that compare to regular concrete? Or those other ideas?
Right, so high-strength concrete, the stuff we use on Earth for demanding applications, typically defined as over 42 MPa.
Okay.
So StarCrete, especially that lunar version at over 90 MPa, is easily in the high-strength concrete range, maybe even beyond typical high strength.
Wow. And compared to the other biopolymers,
Like
Martian biolith,
big difference. Martian biolith was only about 3.6 MPa.
3.6 versus 72 or 92. That's huge.
And those protein binders, they got up to maybe 39.7 MPa, still significantly less than StarCrete.
So StarCrete is dramatically stronger than those other proposed biobinders.
By a significant margin, yes.
What about bending strength? Flexural strength? Does it snap easily?
Good question. Typical concrete usually has a flexural strength between, say, 2.5 and 4.5 MPa. The Martian StarCrete they tested showed about 8.4 MPa, so actually stronger in bending than typical concrete.
Really?
The lunar version was lower, around 2.1 MPa, so more comparable to standard concrete in that regard.
That's genuinely impressive, especially when you think about how simple the ingredients are.
Yeah.
Starch and dirt.
And the relatively low energy process, too, compared to melting rock, for instance.
Right. No extreme temperatures needed, no super complex machinery.
And crucially, the water used in the process, most of it can be recovered. Because the binding relies on dehydration, drying the starch paste out. It's not like cement where the water becomes chemically locked into the structure, so you can potentially reclaim a lot of that precious water.
Okay, let's recap the big advantages then. You've got really high strength. Compressive strength is excellent.
Comparable or better than high-strength concrete.
Low energy needed for production.
Compared to sintering or melting, yeah.
Water recovery is possible. A huge plus in space.
Absolutely critical.
Simple process, uses local resources, the regolith.
And that crucial integration with food production, using surplus starch.
Right, the system integration. Plus, the high strength gives you flexibility in designing structures.
Definitely. Allows for more efficient designs, perhaps thinner walls or different shapes. And there's that one other unique feature, the safety aspect.
You mean the fact that it's edible?
Exactly. I mean, it's a last resort, obviously, a desperate emergency scenario. But if supplies were critically low, starvation was the alternative. The starch binder is food.
That provides a kind of safety net that no other building material offers. Stone, metal, regular concrete. You can't eat those.
It's a remarkable, unique point for mission planning, even if hopefully never needed.
The paper also mentioned using it back here on Earth, didn't it? As a sustainable alternative.
It did, given that cement production is a massive source of CO2.
Huge, like 8% of global emissions or something.
Something like that.
Yeah.
So developing a greener alternative like StarCrete for Earth construction could be really significant. The main challenge there, though, is the moisture sensitivity. Starch binders don't typically like getting wet.
Right, wouldn't work so well for buildings exposed to rain.
No. So you'd need more work?
Yep.
Maybe cross-linking the starch somehow or adding other things like proteins or waxes to make it more water-resistant.
Still, potential there. What about future work in space? What's next?
They mentioned things like optimizing the regolith particle size, maybe even genetically engineering the plants to produce starch that binds even better.
Wow. Custom-designed binding starch.
And adapting the process for things like 3D printing, layer-by-layer construction using StarCrete.
That makes sense for automation.
So yeah, it started with this simple, almost mundane ingredient, starch. But through some really careful research and optimization, they've developed StarCrete. It's surprisingly strong, it's efficient to make off-world, and it has these unique benefits, especially that link between food and shelter.
So you've just gotten a deep dive into a pretty cutting-edge concept for how we might actually build humanity's future beyond Earth, straight from the research.
And it leaves you with a thought, doesn't it? If the very food we grow to survive in space can also build our homes, how fundamentally does that change the whole equation, the design, the logistics of future colonies?
What would a habitat built, quite literally, from surplus potatoes actually look like?
Yeah.
Something to think about.